projects. In this video, we are going to explain about the project title Time Series Forecasting and Modeling of Food Demand Supply Chain based on Regressors analysis. Introduction. The project underscores the significance of accurately predicting customer demand. It's essential for efficiently managing the supply chain as it directly affects a company's financial success. When done correctly, it can lead to cost savings and increased profitability. This point highlights the consequences of getting demand forecasting wrong. Overestimating or underestimating demand can result in issues such as excess inventory, leading to waste and higher operational costs, or stockouts, which can drive customers to competitors. It's mentioned that additional data features like the average base price, maximum and minimum sales per sales center, and sales or orders data per meal have been introduced. These new features are created to improve the precision of demand forecasting models, providing more insights for accurate predictions. This statement emphasizes the critical need for precise demand forecasting in the food industry, where products often have a short shelf life. It also highlights that machine learning, which is adept at handling time-dependent data, is a valuable tool for addressing the challenges posed by short shelf life. This project focuses on the food demand forecasting dataset released by Genpact and compares the effect of various factors on demand. Objective. This project involves using both traditional machine learning and advanced deep learning techniques to predict food demand. The dataset provided by Genpact called Food Demand Forecasting is used as a basis for the prediction task. The primary objective of this project is to understand how different factors impact food demand. It seeks to identify the specific features or variables that have a significant influence on demand patterns. This analysis can help improve the accuracy of forecasting models. In this project, the focus is on using regressor analysis techniques to delve into the data and identify the factors and features that play a crucial role in affecting food demand. Regressor analysis helps establish relationships between predictors, features, and target variables demand and quantifies these relationships. The project involves comparing 7 different regression models, with one of them being LSTM, long short-term memory, which is a deep learning technique commonly used for sequential data. The project's findings demonstrate that LSTM outperforms the other regressors for ordering forecasting, indicating its effectiveness for the specific task. To assess the performance of the forecasting models, the project uses various evaluation metrics such as RMSLE, root mean square logarithmic error, RMSE, root mean squared error, MAPE, mean absolute percentage error, and MAE, mean absolute error. These metrics help measure the accuracy and reliability of the models in predicting food demand. Software and hardware requirements of the project are: hardware requirements are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are: application is Anaconda, primary language used in the project is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. In this module, the project starts by importing the necessary software packages and libraries. These packages typically include Python libraries like Pandas for data manipulation, NumPy for numerical operations, sklearn for machine learning, and potentially deep learning frameworks like TensorFlow or PyTorch. These packages provide the tools and functions required for data analysis, modeling, and more. Exploratory data analysis. This module involves exploring and understanding the dataset. It includes tasks like data visualization, summary statistics, and data cleaning. Exploratory data analysis (EDA) helps project stakeholders gain insights into the dataset's characteristics, distributions, outliers, and relationships between variables. Data pre-processing. Data pre-processing is the step where the data set is cleaned, transformed, and prepared for analysis. This can include handling missing data, scaling or normalizing features, and any necessary data transformations to make it suitable for modeling. For time series forecasting, this might involve handling date-time data and creating lag features. Label encoding using label encoder. Label encoding is used to convert categorical labels into numerical values. This allows the model to work with the data more effectively. Splitting the dataset into train and test. Data is typically divided into two parts, the training set and the testing set. The training set is used to train the forecasting model, while the testing set is used to evaluate the model's performance. This separation ensures that the model is tested on data it hasn't seen during training, providing an unbiased assessment of its accuracy. Building the model. In this module, the forecasting model is constructed. For time series forecasting, this can include traditional statistical models like ARIMA or more advanced machine learning models like regression analysis, decision trees, or even deep learning models like LSTM, long short-term memory. Training the model. The model is trained using the training dataset. For time series forecasting, the model learns from historical data patterns and relationships to make predictions about future demand. Training may involve tuning hyperparameters to optimize the model's performance. Flask framework with SQLite for sign-up and sign-in. This module suggests that the project includes user authentication and management. Flask is a web framework for Python and SQLite is a lightweight database. These are used to implement user sign-up and login functionalities in the project, ensuring data security and access control. The given input is pre-processed. This step likely refers to pre-processing incoming data from users or external sources before using it with the forecasting model. It ensures that the user-provided input is clean and formatted appropriately for the model's input requirements. The trained model is used for prediction. After training the forecasting model on historical data, this module involves applying the trained model to make predictions on new or future data. In the context of food demand forecasting, the model would use its learned patterns and relationships to predict future food demand. Final outcome is displayed. The results generated by the trained model are presented to the project stakeholders or users. This could be in the form of graphical visualizations, reports, or numerical predictions. The final outcome provides insights into what the model predicts for future food demand. This module indicates that, as an extension to the initial modeling efforts, an ensemble model is employed. Ensemble models combine the predictions of multiple models to improve accuracy and robustness. By using an ensemble approach, the project aims to enhance the reliability and accuracy of food demand forecast. The ensemble model's predictions are used as the final predictions for the project. Algorithms used in the project are random forest. Random forest is an ensemble learning method that combines multiple decision trees to make predictions. It improves the accuracy and generalization of individual trees by averaging their outputs. Random forest can be used to predict future food demand by using historical time series data as input features. It can handle various types of data such as weather conditions, holidays, and historical sales to make predictions for future demand. Gradient boosting. Gradient boosting is another ensemble learning technique that builds a strong predictive model by training weak learners sequentially. It minimizes the error of the previous model at each step, creating a powerful predictive ensemble. Gradient boosting can be used to improve the forecasting accuracy of food demand by iteratively building predictive models that account for complex relationships in the time series data. Light GBM. Light GBM is a gradient boosting framework that focuses on speed and efficiency. It uses a histogram-based learning algorithm and can handle large datasets and high-dimensional features. Light GBM can be employed for time series forecasting in situations where efficiency is critical, such as large-scale food supply chain modeling and forecasting. CAD Boost. CAD Boost is a gradient boosting library specifically designed for categorical features. It automatically handles categorical variables and can deliver competitive performance. CAD Boost can be used in the food supply chain modeling project to handle categorical features such as product categories or geographic locations that are important for predicting food demand. XGBoost. XGBoost Extreme Gradient Boosting is a popular gradient boosting library known for its efficiency and predictive power. It is used in various machine learning tasks including regression and classification. XGBoost can be applied for forecasting food demand in the supply chain by creating an ensemble of decision trees that can capture complex patterns in the time series data. LSTM, Long Short Term Memory. LSTM is a type of recurrent neural network (RNN) designed to handle sequential data. It can capture long-term dependencies and is particularly effective for time series forecasting. LSTM can be used to model and forecast food demand in the supply chain based on past time series data. It can capture patterns and dependencies in the data over time. BiLSTM, Bidirectional LSTM. BiLSTM is an extension of LSTM that processes the input sequence from both directions, which allows it to capture dependencies in both past and future data points. BiLSTM can be used for food demand forecasting by considering the influence of both past and future data, potentially improving the accuracy of predictions. CNN, Convolutional Neural Network. CNN is a neural network architecture primarily used for image processing. However, it can also be applied to time series data by treating it as an image and extracting relevant features. CNN can be used to analyze and forecast food demand time series data by extracting spatial patterns, detecting trends, and capturing important features in the data. We have used CNN as an extension. Comparison graph. This is the MAE comparison graph. On the x-axis, we have the MAE score, and on the y-axis, we have the algorithm name. MAE is a metric that calculates the average absolute differences between the predicted and actual values. It provides a straightforward measure of the average magnitude of errors without considering their direction, overestimation, or underestimation. This is the RMSE comparison graph. On the x-axis, we have the RMSE score, and on the y-axis, we have the algorithm name. RMSE, root mean squared error, is a common metric that calculates the square root of the average square differences between the predicted and actual values. It quantifies the average magnitude of the errors in forecasting. A lower RMSE indicates a more accurate model. This is the MAPE comparison graph. On the x-axis, we have MAPE score, and on the y-axis, we have the algorithm name. Mean absolute percentage error. MAPE calculates the average percentage difference between the predicted and actual values. It provides a measure of the accuracy of the forecast in terms of percentage errors. MAPE is useful for understanding the relative accuracy of forecasts, especially when dealing with a range of values. This is the RMLSE comparison graph. On the x-axis, we have RMLSE score, and on the y-axis, we have the algorithm name. RMLSE, root mean squared logarithmic error. RMLSE is a metric that measures the average logarithmic difference between the predicted and actual values. It is particularly useful when there is a wide range of values in the dataset. RMSLE penalizes underestimations more heavily than overestimations. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the dataset folder. This dataset folder contains the test data. Importing the test data contains the information of ID, week, center ID, mail ID, checkout price, base price, emailer for promotion, etc. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model folder, which contains algorithm information which will be loaded into the project code during runtime. This is notebook file. This Jupyter notebook file contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I am copying the path. Open Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. Here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I am copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The home page of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have created and then click on sign in button. So here we have logged in successfully. We need to enter all these parameters. So I'm entering the parameters. So here I have entered all these parameters. Week is 1. Week represents the time dimension for understanding temporal demand patterns. Center ID is 89. It identifies the specific distribution center impacting demand based on location. Mail ID is 2640. It differentiates between mail types, each with unique demand characteristics. Checkout price is 281.33. It reflects the selling price, a key factor affecting customer demand. Base price is 280.33. It represents the standard cost, influencing demand, especially with pricing strategies. Emailer for promotion is 0. It indicates the use of promotional emails affecting demand through marketing efforts. Homepage features is 0. It signifies homepage promotions potentially influencing customer orders. City code is 703. It categorizes distribution center locations, accounting for regional demand differences. Region code is 56. It identifies the region, providing insights into regional variations in food demand. Center type is 0. It classifies the distribution center type impacting operations and demand. OP area is 4.8. It identifies the operational area influencing the scale and demand patterns of the center. After entering all these parameters, click on predict. So here we got the result as 4.560. The primary goal is to predict or forecast food demand. The conclusion of the project is This point underscores the critical importance of precise demand forecasting in the food industry, where products often have a limited shelf life. Accurate forecasts are essential for effective supply chain management, ensuring that the right amount of products is available at the right time, reducing waste and preventing stockouts. The result of the project demonstrated the potential of deep learning models, particularly LSTM, in accurately forecasting the number of orders. LSTM outperformed other algorithms in terms of forecasting accuracy. Evaluation metrics such as RMSLE, RMSC, MAPE, and MAE were employed to assess the forecasting model's performance. The project used a set of evaluation metrics including root mean squared logarithmic error, RMSLE, root mean squared error, RMSC, mean absolute percentage error, MAPE, and mean absolute error, MAE, to assess how well the forecasting models performed. These metrics provided a quantitative measure of accuracy and reliability. In this point, it's mentioned that new data features were created to enhance the accuracy of forecasting models. These new features include the mean of base prices and sales or orders data for each meal, among others. These additional attributes provide more information to improve the precision of the forecasting process.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.